everyone, I'm Sherry and welcome to my channel. Today we are going to tackle a fascinating and intriguing LeetCode Daily challenge, maximum profit in job scheduling. This is a great problem to understand dynamic programming and binary search, and it's definitely one of my favorite problems among all daily challenges. So let's now dive right in. First, let's understand the problem. We are given three arrays representing start times, end times, and profit of jobs. Our task is to find the maximum profit by scheduling jobs without overlapping in time. Now, this problem might remind you of the classic interval scheduling problem, but with a twist here. We have to consider profit. So we're not just trying to fit as many jobs as we can, but also maximize the profit. Let's walk through this example to understand the requirement better. We are given arrays for the start times, end times, and profits for various jobs. We need to select jobs such that no jobs overlap, and we maximize our profit. As illustrated, we have jobs starting at times 1, 2, 3, and 3, with corresponding end times 3, 4, 5, and 6, and profits 50, 10, 40, and 70. To maximize profit without overlapping, we select the first job with a profit of 50 and the first job with a profit of 70. The total profit is 120, which is the sum of 50 and 70. After solving this test case, we have the following observations. First, current job decision will affect our future job choices. Here, if we take the second job, starting at time 2, then we are not allowed to take the third or the fourth job, and thus losing profit. Second, we can't just pick the job with the highest profit or greedily aiming for a higher profit sum at each step. We must consider the schedule confliction. Based on these observations, we find this question an excellent candidate for dynamic programming. Why? Because dynamic programming is excellent for optimization problems where decisions depend on previous choices. We will sort the jobs by their starting times and use dynamic programming to find the best combination of the jobs. Now, let's do a brief walkthrough of our dynamic programming solution. If you feel confused or think this walkthrough is too abstract, don't worry. We will have a detailed example walkthrough with great illustrations right after this part. So stay tuned and let's discuss this solution together. First, we sort the jobs by their start times. This ensures that when we process the job, all possible previous jobs are already considered. Then, we create a recursive function with memorization, which is our dynamic programming. We will first create a dynamic programming function named maxProfit that returns the maximum profit attainable from the ith job to the end. We will use memorization to store the result of subproblems to avoid recomputation. Among the jobs choices available to us, for each job we have two options. First, we could take the current job, which means that our profit sum would be profit of our current job, which named here as current job profit, plus the max profit starting from the non-conflicting next job index. Or we can choose to skip our current job. Then our profit sum would be 0 because we are not doing our job, we are receiving 0 profit for this job, and plus the max profit starting at the next job index. We return the higher profit sum among the two options as the maximum profit attainable from the ith job to the end. To return the answer to the problem, we finally call maxProfit 0 to return the maximum profit attainable from the very beginning 0th job to the end, so that we covered every jobs in our jobs list, and we thus come up with the best combination, generating the maximum profit. We also have a few optimizations that we can do to the above solution. First, we can do the binary search. We will use binary search to find the next non-conflicting job index because if we want to find the next non-conflicting job index by walking through the array, this action will actually take all of n time, while binary search only takes all log n time. The second optimization we can make is to transition our top-down dynamic programming to a bottom-up dynamic programming Because the top-down solution uses recursive DP function so that by using the iterative bottom-up DP, we save the recursion overhead, even though theoretically, both the top-down DP and the bottom-up DP take the same time complexity and space complexity. Let's solve the same test case as before, but with our dynamic programming solution. We will walk through the solving process using grid illustrations as I promised you, so that we can make our solution crystal clear. As you can see, I have processed the input arrays a bit so that the jobs are sorted by their start time. Here, I want to state my secret weapon of solving dynamic programming questions. Think small and consider base cases. Then, we gradually expand our consideration range using recurrence relationship. Let's see how we can apply this to our question. To start, we consider about our base case. At the very beginning, when we have no jobs left or no jobs available to us, we hit the base case because if we have no jobs to do, then the maximum profit now would be just 0, so that we can simply put a 0 to the maximum profit starting at index length of jobs. Now we add one more job to our consideration range, and now since we have one job available, we need to apply our recurrence. As illustrated in the solution walkthrough, we know that the maximum profit we can make is the higher profit among the two options, take current job or skip the current job. In this case, we can take the current job at index 3 and thus have a current job profit at 70, or we can choose to skip this job and having a profit of 0. Therefore, we choose the higher profit, which is 70, and thus we place 70 at index 3 of our DP max profit array. By recording our computation result, we are guaranteed that we never compute a subproblem choice. We now add the job at index 2 to our consideration range, and then we will consider what is the maximum profit that we can gain if we have jobs starting at index 2. Well, if we take index 2, this means that we are not allowed to take any other jobs in our list because taking other jobs will cause a time conflict. Therefore, the profit we can gain by taking this job is just 40, while at the same time, if we just choose to skip this job, we can have a profit of 70. We choose the higher one, which is 70, and we put 70 at index 2 of our max profit array. We will now expand our consideration range furthermore. If we add job at index 1 to our consideration range, for job at index 1, if we take this job, then we're not allowed to take job at index 2 or index 3 because this will cause a time conflict. Or we can choose to skip job at index 1 so that we can gain the max profit starting at next job index, which is 2. Therefore, we take the higher one, which is 70, and place it into the index 1 of our max profit. Finally, we add our last job in our list, our job at index 0, into our consideration range. For job 1, if we take job 1, then we can see, besides taking job 1, we are still allowed to take other jobs without creating any time conflict, so that our max profit would now be 50 plus 70, which is 120. And if we choose to skip this job, we are going to have a profit of only 70. Therefore, we take the higher one, which is 120, and put it into the 0 index of our max profit array. Eventually, we will return 120 as the final answer. Now, let's analyze the time complexity and the space complexity of our DP solution. The time complexity of our DP solution would be O of n times log n, because first, we sort of jobs by the starting time, which takes O of n times log n time. Secondly, we do our DP function calling, and because we have n subproblems in total, each subproblem calls max profit function 2 times. And also, non-memorized max profit call takes O of log n time because we are doing the binary search, while a memorized max profit only takes constant time because the result is already memorized in our hash map or a button-up DP array. Therefore, in total, n subproblems take O n log n plus n time, so that we have an overall time complexity O of n log n. The space complexity would be O of n because storing the start time, end time, and profit of each job takes O of n space, and also DP memorization or tabulation also takes O of n space because we need to record the result of n subproblems. Now let's get to the real code and see how we can implement our dynamic programming solution. First, we will see the top-down DP solution. We sort our jobs by starting time and initialize our DP hash map. We extract start times for binary search. Also, we define our binary search helper function to help find the next non-conflicting job index. Now, we will implement our top-down DP recursive function. First, we state our base case when we reach the end of job list so that we have no jobs available. Then we will just return 0 as the maximum profit because we cannot do anything. Then, since we are using dynamic programming, before we do anything, we need to check if our computation result is already computed and stored in our memo, so that we do the if check. If the current index is not in our memo, which means that we need to do this fresh computation. As we explained before, we will compute the profit earned if we take our current job or if we skip our current job, and then take the higher one to store in our memo. Finally, we will call our DP function to our overall question. We call max profit function with index 0 so that we cover all the jobs in the jobs list in our consideration range and return the best combination which generates the maximum profit. As you can see on the left, I have already marked some improvement that we can make. Here, binary search function is defined by us, but if you're using Python, this can be replaced with bisect function in Python. Also, if you want, you can also do the memory part using the least recently used cache provided by Python, but that would be too language specific, so that I would not cover it here. Also, we can implement bottom-up DP to avoid the recursion overhead. Here is the code of top-down DP with bisect in Python just in case you're interested. Eventually, let's see how we can implement a bottom-up DP. The logic is exactly the same as we did in our top-down DP, but here we are doing an iterative call. I strongly encourage you to try out both top-down and bottom-up DP by yourself because it will be a great exercise of implementing dynamic programming. Alright, that's the end of today's daily challenge. In this challenge, we practice binary search and dynamic programming. This question is rated as hard, possibly because it takes practice to implement binary search and dynamic programming fast and correctly under the stressed interviewing context. By watching this video, I believe you can crack similar problems with confidence and ease in the future. I'm Sherry, thank you for watching. I hope you enjoyed this video, and I will see you in the next daily challenge tutorial. Bye bye!